So welcome everybody. We're delighted to have you here. This is CoreAVI's webinar, Vulkan, the Future of Embedded Graphics. My name is Mary Beth Behrens and I'm the Director of Marketing here at CoreAVI. The webinar is going to be given today by our FAE, Lucas Friesick. So I ask again that you make sure that you're on mute because we are recording it, so we want to minimize any kind of background noise. And please keep your questions until the end. Lucas will give time at the end to answer anything you might have. Okay, I think that's it. And Lucas, it's all yours.
Thank you very much, Mary Beth. So thank you all for coming. Today's presentation is a general overview of what Vulkan is and why it is a good fit for the future of embedded graphics. I also will go into a comparison between the differences between Vulkan and OpenGL as well. So let's dive right into it. What is Vulkan? So Vulkan is the next generation of graphics and compute APIs from the Khronos organization. So for those who are not familiar with what Khronos is the standards body that develops open standards for GPUs. They're most well known for OpenGL and OpenCL. And all of the standards that they develop are publicly available on their website. So on this slide at the bottom, I included a link to the Vulkan registry that has the Vulkan standard as well as header files and the documentation and tools associated with Vulkan. So to get a little bit more detailed into what Vulkan is it is an API that provides programmable GPU shaders and pipelines. So what that means is it provides programmable access into the GPU through shaders and through programmable pipelines. So people who are familiar with OpenGL probably know what a programmable shader is. It's a block of code that you can use to control how the GPU will handle vertex transformations or fragment processing or geometry processing. The addition of pipelines lets you control how data is basically moved around the GPU. So when you're starting your rendering operation, you can control how textures are copied in or memory is moved from one area of the GPU to another. So this gives a kind of another layer of programmability that wasn't previously exposed in OpenGL. So in OpenGL, specifically the safety critical standards, there's only support for vertex and fragment shaders in OpenGL SE. Vulkan expands this support of programmable shaders to vertex, fragment, geometry, tessellation, and even general purpose compute shaders. So what that means is Vulkan can be used for all the things that you used OpenGL for with vertex and fragment processing, but you can also do more advanced graphics techniques such as tessellation and also general purpose GPU compute with the use of GPU compute shaders. And that leads to the point at the bottom that the GPU can be both used for compute and graphics at the exact same time. So Vulkan exposes the ability for data that has been used in a compute operation to be used in a graphics operation seamlessly. The way that both shaders interact with the data is exactly the same, so they can both access it, operate on it, and use it and have a seamless experience. So to better illustrate what Vulkan is, I'm going to compare it to OpenGL and what features Vulkan has versus what features OpenGL has.
Mark Chester
is now joining.
So on the left, we have features supported by Vulkan, and on the right, we have features supported by OpenGL. A big point in the comparison between Vulkan and OpenGL is that Vulkan is much more low level than OpenGL. Vulkan takes an approach where it's trying to have the most portable, but also the lowest level layer on top of the GPU so that the same code can run across different GPUs, but there's very little overhead to running that code. Later, I'll go over kind of how this is achieved in how the lower level layers of Vulkan work. But just for now, Vulkan is a lower level API than OpenGL. Vulkan provides both graphics and compute capabilities, while standard OpenGL, especially OpenGL Safety Critical, only provides graphics capabilities. Vulkan gives full control over GPU pipelines and shaders, where in OpenGL, the driver you are using handles the GPU pipelines. And if you're using a graphics API like OpenGL SC 1.0, the shaders are also handled by the driver for you. So you don't have control over how they're implemented or if they're a good fit for your application. The consequence of this is that more setup code is required since you need to build up your own GPU pipeline and shaders versus in an OpenGL driver, the driver developer would have handled all that setup for you. Vulkan is a stateless API, so it's designed with multi-threading in mind. What this means is since there is no global state within the Vulkan API, multiple threads can act on Vulkan primitives and not have to worry about corrupting the state of a different thread. The Vulkan spec also calls out how things can be multi-threaded with multiple threads running on different cores, building commands for the GPU to execute in parallel. The last point about Vulkan, which is a very big difference than OpenGL, is error checking and validation of how the API is used is not handled by the driver at all, versus in OpenGL, it's mandatory that the driver implements error checking and validation. So what this means is error checking can be added in as a separate layer, which is completely supported by Vulkan, and then stripped out when you have a release build. And the benefit of that is in a development build, you'll have all the debugging information you need about when you're using APIs wrong or using interfaces wrong. But when you have a release version that you're putting on a production system, you can strip out those error checks so that you don't have the overhead on the CPU of validating the data before it goes to the API. Whereas in OpenGL, you're forced to have this validation at all times, so you can't remove it if you need a small performance gain. So to further elaborate on the differences between Vulkan and OpenGL, the API of OpenGL, you may have heard of it referred to as a narrow API. So what this means is that it has fewer functions that provide more complex behavior. So if you think of the width and length of the API as being how many functions it has, and the height being how complex those functions are, OpenGL functions are much more complicated, so they're a lot deeper, but the amount of functions that it provides are much smaller. So for example, in OpenGL SC1, there's approximately 127 functions provided that each implement complex behaviors that interact with the GPU shaders, the GPU pipelines, the GPU state, and moving data between different areas of the GPU. Whereas in Vulkan, it's considered a wide API where there are many functions that implement small single behaviors that are not as complicated. So to better illustrate that, Vulkan has 351 functions approximately in the core Vulkan spec, and these functions have a single purpose. So for example, there's a function to move data between one area of memory to another. So whereas in OpenGL, you would, if you wanted to copy data from one area to another, and the data was texture data, you would call the function to move texture data, and it would handle making sure that all your buffers are created, that they're large enough to hold the data, and then finally copy them over, probably using DMA engines in the GPU. Whereas in Vulkan, you have full control over how that copy is implemented. You could do it completely on the CPU. If you're not trying to overburden the GPU, you could implement it using DMA on the GPU. You control how big the memory buffers are. So the actual API is a lot smaller, but you need more code around it to implement the function that you want to complete. So to get more in depth about the differences, At a high level, OpenGL works with a global state machine. Rendering is based on this global state. The different functions in the API modify the global state, and then there's basic primitives for memory management with textures, vertex buffers, shader programs, and all of that. But at the end of the day, you're at the mercy of the driver for how all of that is implemented. So to give an example or better illustration of what this slide means is that in OpenGL, there's a global state that exists in the program that represents what the GPU is going to do when you tell it to draw. This state contains information about what shader program you want to use, or what depth test you want to use for 3D rendering, or what the current texture you want to draw is, or what the current lighting values you want to use are. And that state is stored implicitly and globally in the application. And when you call a function that is supposed to do something that draws, so for example, the function glDrawArrays, it's going to read that global state and then perform the drawing operation based on that global state. And so the functions OpenGL provides are memory management functions, global state modifying functions, and then the drawing operations. Now, if we oppose this to Vulkan, there is no global state in Vulkan. The way the driver functions is that you acquire resources from the hardware and then you operate on them. So you ask the hardware for some kind of resource. This could be a memory resource, a command queue or a command buffer, a pipeline resource, and then that holds the state of the drawing operation you want to perform. So if we use the example of changing the depth or the color that we want to draw with, in Vulkan, what you would do is you would make sure that there's memory associated with where you want to store the color to draw with by acquiring a memory resource for it. You would create a command queue to execute your command buffer. And inside your command queue, you'd put a drawing operation that reads from where the color value is stored. And that would all get compiled into a pipeline, and you'd execute that command buffer using that pipeline. And it would draw using that entire chain of events that you set up. Whereas in OpenGL, you'd have a function that changes the global color value, and then you draw, and it'll draw using that global color value. So from that, you can see that Vulkan definitely is a lot more complicated, but the functions it's providing map directly to features provided by the hardware. And this is an important distinction because Vulkan is basing the way it works on how GPUs are implemented in the modern day. So if we look at a timeline of graphics APIs and when they were released, we can see that the original OpenGL 1.1 spec was released in 1997. And so that API was based on assumptions about how GPUs worked back in 1997. And the consequences of that are that any API that is based on OpenGL 1.1 will have those same assumptions baked into it. So if we look, OpenGL 1.3 was released in 2001. This is the standard that OpenGL SC is based on. But OpenGL SC was not released until 2005. So OpenGL SC is making assumptions about how the GPU works based on a standard released in 2001, which means it's not entirely reflective of how GPUs do things anymore. So when you execute a command in OpenGL SC1, there's a high likelihood that that command needs to be emulated at least somewhat in software to reflect the changes that have happened in GPU hardware over the last decade. If we continue, we can also see OpenGL ES2, which is the standard OpenGL SC2 is based on, was released in 2007. And then in 2006, OpenGL SC2 standard was ratified, and the Vulkan standard was also ratified then. So from that, we can see that OpenGL SC2 is making assumptions based on how GPUs worked in 2007, and Vulkan is now making assumptions based on how GPUs function from 2016 onward. Sounds like someone's off mute. Could they please mute their microphone? So to kind of, I guess, beat down the point, Vulkan reflects how modern GPUs function. So all these lower level commands that do memory management, they at the driver level aren't very complicated. They basically reflect a one-to-one mapping on how the GPU is, or the GPU hardware expects to do that operation. So what this means is you have less driver overhead in order to implement the graphics functions you want. This leads to less CPU overhead, which reduces power usage since the GPU is idling for less time. And the other benefit of this is that since GPUs have gotten more programmable, you can use the GPU for more than just graphics. So general purpose GPU compute is now an option since the programmable aspect of the GPU is now exposed for general purpose operations. And the stateless API allows for multi-threading or multi-core usage of the GPU, where you have multiple threads on different cores building commands in parallel for the GPU to access, so that the GPU is not bottlenecked by how quickly the CPU can give it work to do. The other benefits of Vulkan the other benefits of Vulkan is that it's such a low-level API that you can build other graphics APIs on top of Vulkan in a way that's GPU agnostic. So for example, OpenGL SC1 can be built on top of Vulkan, and we've actually done that with our VK Core GLSC1 product. And OpenGL SC2 can also be implemented in Vulkan, and we've done that with our VK Core GLSC2 product. So the key benefit with that is if you've been listening to the presentation, Vulkan is a lot more complicated in how simple graphics operations are completed, since it exposes things at a much lower level. So if graphics is a means to an end for you, you just need to display something on the screen, then using a graphics API like OpenGL SC2 on top of Vulkan allows you to quickly build the graphics application while still giving you the option to use Vulkan in the future for perhaps general purpose GPU compute, or if parts of your graphics application are too slow, then you could take an approach of re-implementing in Vulkan and then compositing the results between OpenGL SC2 and Vulkan in a single application. Really, the options are endless. It's a pretty flexible system that allows kind of the best of both worlds, where you have a simpler API to get started quickly with the option of having the full performance and capabilities of the GPU being exposed to you with Vulkan. And lastly, the Vulkan benefits for embedded systems really are complete control over memory management. Embedded systems are usually low resource systems. They don't have a lot of RAM, or they don't have a lot of CPU power. And since you have complete control over memory management on the GPU, you can make full use of that RAM. The application developer knows best what they need to store in memory for their graphics application, and having undivided access to that RAM lets them, choose how they're storing things to make sure that they actually have access to, for example, the 4 gigabytes on an E9171. Likewise, since the CPUs are not as powerful, computation can be offloaded to the GPU. This leads to better utilization of system resources. So embedded systems are usually low power devices that potentially run on a battery. And if you can make better utilization of your system resources, parts of the device can be underclocked or have their power usage reduced or go into low power sleep modes, which means that they won't be running at peak power for the entire operation. And this leads to better battery life or running a cooler system, which is a requirement for a lot of embedded systems. And the last key benefit is more of just a software development one, is the availability of simple graphics libraries that allow you to set up graphics easily and quickly. So like I mentioned before, OpenGL can be implemented on top of Vulkan. We have a product that allows customers to implement OpenGL applications on top of Vulkan so that they can get set up quickly and easily, and then when needed, they can switch over to Vulkan for any benefits they need for reduced RAM usage, reduced better utilization of system resources, and offloading computation to the GPU. So that covers what I wanted to talk about for what is Vulkan and why it's the future of embedded graphics. If there's any questions from the audience, please let me know and we'll answer them. If any comments, questions, or feedback that you'd like to provide.
Okay, well, doesn't sound like anybody's got any questions or comments. You can always email Lucas after the webinar, and he can answer something if you think of something later. Other than that, I guess we've finished for this one. So thank you everybody for joining us. We've got a series of these webinars going on. The next one is June 16th at the same time, and it's Next Generation Graphics, GPU, Shader, and Compute Libraries. That one's going to be given by our Senior FAE, Bob Pickle. So we hope you'll join us for that one as well. Okay. Thank you very much. We hope to have this recording up online soon, so you can rewatch it as well. Have a great day, everybody.